Welcome back to Alpha Learning session 24. Almost elimination reactions, last part this one. Today we are going to discuss a different type of elimination. Previous session we discussed that E2 and E1 elimination. Now let us see this example. RCH2CH2Br, which is a primary alkyl halide. This one upon reaction with ethyl alcohol. Generally we are getting ethyl alcohol, we are getting substitution product ether, alright, that is SN2 mechanism it follows. And when we are using ethoxide ion in case of ethyl alcohol solvent, means alcoholic base which leads substitution, which leads elimination, right? Now if it is ethyl alcohol, it leads substitution. If it is ethoxide ion, it leads elimination. That is very clear. So in elimination, which elimination it prefers? Obviously we can expect that this bromine containing carbon, alpha carbon, adjacent carbon, beta carbon consists hydrogen. Obviously this C2H5O minus command attack upon beta hydrogen, and it leads E2 elimination concerted mechanism generally we are expecting. Now practically or experimentally, when I am going to use deuteroethyl alcohol as solvent, final product what I am going to get here is RCD double bond CH2. This is the final product. How it is possible? In case of ethoxide ion, if it acts as a nucleophile, obviously it has to displace Br. Whereas if the same ethoxide ion, if it approaches to beta carbon containing hydrogen, it has to give elimination. Fine. In elimination we should get RCH double bond CH2. From here hydrogen, from this carbon Br. So beta elimination has to take place and we are getting alkene. But from where this deuterium you are getting? So in order to predict the mechanism, let us see what happened here. This ethoxide ion has to abstract hydrogen from here. Then we are getting RCH minus CH2Br. So alpha, this one is haloalkane. With respect to this haloalkane, this beta carbon containing hydrogen is acidic. So that H plus it abstracts, and resultant we are getting here conjugate base. This is conjugate base. This conjugate base is going to abstract proton from solvent, which is deuteroethyl alcohol. It is going to abstract this deuterium. Resultant we are getting RCHD and CH2Br. This one here, what remains here? C2H5O minus remains. That C2H5O minus again abstracts proton. C2H5O minus again abstracts proton from here, and which leads RC minus here D CH2Br. Now here elimination takes place like this. So what happened? Once again have a look. Ethoxide ion first abstracts proton from beta carbon containing hydrogen, beta carbon, and it leaves carbanion. As I mentioned that carbanion, formed carbanion is nothing but conjugate base. This conjugate base, being a base, it abstracts proton again from solvent. But here solvent is deuteroethyl alcohol. So from that D plus it is going to abstract. Now it has a C. This beta carbon possesses hydrogen and deuterium both. Hydrogen and deuterium both are there. Now this deuterium CD bond requires more energy for breaking compared to CH bond, right? So when again this ethoxide ion acts as a base, it is going to abstract a proton from here. That means in first step displacement of H plus with D plus, and in second step there is no more possibility here, and a little amount of C minus participates in elimination. So here this minus turns towards this one, and since this Br will leave away. So whenever this Br leave away, here these electrons comes like this, then the resultant double bond or pi bond formation between these two carbon atoms, we are getting alkene. So this is the product what we notice. That means beyond of that what we learn E1 and E2, there is one more possibility for elimination, that is what we called elimination unimolecular from conjugate base. That is simply noted as E1 CB elimination. Elimination unimolecular from conjugate base. So that 1 indicates unimolecular reaction, CB indicates conjugate base, E indicates elimination. This type of elimination what we called E1 CB elimination. Is it real? Is it real? So how can you say that? So in order to identify that, I am going to consider one more example here. In this example, here leaving group is OH group. Leaving group is OH group. Real sir, you only mentioned earlier elimination reactions. OH group is a poor leaving group. Yes, obviously. OH minus is poor leaving group. No doubt in that one. OH minus is poor leaving group. But how it is possible? Let us see here. So basically, leaving group is not a good leaving group. But we make it compulsion to leave away. I am repeating once again. It itself do not have any tendency to leave. Such type of tendency containing groups what we call the good leaving groups. But here what I am saying, OH is poor leaving group. So in case of E1 elimination, we make that OH protonation and converts into OH2 plus. Further it makes good leaving group. But here not like that. What we are doing here? Still we are giving base. That means basically this OH has less leaving tendency or less nucleophugacity. But we make compulsion to leave that leaving group. How? By using again base OH minus. Okay, right now K plus and OH minus or OR minus, whatever it may be, strong base we are considering, that OH minus prefers to abstract proton. From where it can abstract proton? So this OH group, from here it can abstract proton. Let us check. If it abstracts, this OH minus abstracts proton from this OH group and leaves O minus. Now my question is, can O minus stabilize itself? In other words, that negative charge which appears upon oxygen, is there any chance to participate in resonance structure? In other words, can anybody is going to accept that negative charge? Here this carbon, this carbon, this carbon, no one, right? That means this O minus is not that much stabilized. So this OH minus abstracts proton, where resultant negative charge can be stabilized. Because in other words we can say, where negative charge can be stabilized, that particular hydrogen is more acidic. Now here with respect to this C double bond O, this carbon what we call alpha carbon, and this alpha carbon containing hydrogens are acidic. This alpha carbon containing hydrogens are acidic. Now OH minus abstracts a proton from here. Have a look here, what happened here? C double bond O, OH. This one upon treatment with OH minus, this OH minus abstracts proton from here and leaves carbanion. So you only mentioned that, sir, how can we say, is it stable? Yes, because of it is involving in resonance with C double bond O. Why this hydrogen only acidic? Resultant formed carbanion or negative charge can be stabilized with respect to C double bond O. Hence, in this case, one more resonance structure what we are getting is O minus, here double bond formation, here OH, like this we are getting. Now, whenever this negative, these two are interconvertible resonance structures, because of resonance this carbanion can be stabilized. And in other words, we can say after abstraction of a proton by base, whatever we are getting, that is conjugate base. Now this conjugate base from here, if these electrons comes like this and this OH has to leave away, resultant we are getting product. So this one with respect to C double bond O, alpha and beta, the newly formed pi bond is more stable because of it is in conjugation with C double bond O. Hence it is more stable. We got elimination product. Here OH comes out as OH minus. Yes, OH minus came out. OH minus acts as a leaving group. But how it acts as leaving group, sir? It is poor leaving group now. Yes, we can make that poor leaving group into good, because by making this carbon, adjacent carbon is electron rich. So because of this carbon is electron rich and this carbon consists negative charge which is stabilized because of resonance, in such a case this negative charge will be shifted towards adjacent carbon and OH has to leave away as OH minus. So if it is looks like E2 elimination, it looks like E2 elimination. In E2 elimination what happened? Somewhere base OH minus has to come and abstract proton and these electrons goes like this OH has to leave away. It looks like. But if it is so, sir, why you write this mechanism? This mechanism is not experimental one. This mechanism is only hypothetical one and predicted one. But it should prove that experimental aspects, whatever we are expecting, that should coincide with experimental aspects. I used to propose this mechanism. Myself propose this mechanism, suppose. Now I am going to ask, or you are going to ask, sir, why like that? I am going to say, I am going to explain the same product like this. OH minus has to come and abstract this proton, okay? Because of you only mentioned this hydrogen is more acidic, accepted. So OH minus abstracts the proton, right? And this CH sigma bond electrons will be shifted towards next carbon, okay? And OH minus has to leave, okay? Let us think like that. So that will happen if leaving group is good leaving group. If leaving group is good leaving group, yes. If leaving group is good leaving group, whatever you said that is correct. But here you mentioned that OH minus is poor leaving group. In such case also you are getting this product. In such case also you are getting this product. Means even though leaving group is poor leaving group, we are getting this product. It means that it is not quite regular E2 elimination. Now, if it is observed here, first step, whatever here happens, that is a fast step. Because abstraction of a proton, that is acid-base reaction, much fast. And departing leaving group and shifting this negative charge, this one is a slow step. Obviously slow step is a rate determining step. So in rate determining step, what do you say? R is equal to K into what you have to write? This conjugate base. Here elimination leads from conjugate base but not from this substrate, right or not? So R is equal to K into concentration of conjugate base power 1. That means it is a unimolecular reaction. Only conjugate base is going to take part in the elimination step, slow step, rate determining step. So conjugate base only participated, hence we are saying it is unimolecular. But it looks like biomolecular. But it is unimolecular. Looks like biomolecular elimination. Experimentally it is unimolecular. That's why E1 from conjugate base, that's why E1 Cb. So rate is equal to K into conjugate base concentration whole power 1. But conjugate base is intermediate. It is not reactant practically. It is one of the intermediate. In rate law, you are not supposed to write that intermediates, carbocations, carbanions. We are not supposed to write. So instead of that, what we have to write? From where that carbanion you are getting. That carbanion formation takes place from where? Which type of, which reactants? That carbanion takes place, the carbanion formation takes place from base and substrate. From base and substrate. That's why what we can write? Rate is equal to, so rate is equal to K into substrate and base. So shall we write this one as rate law? No, you are not supposed to write. Rate law is this much only. But instead of conjugate base concentration depending upon base concentration. Now what I am trying to explain here is, if you increase base concentration, conjugate base concentration increases. If you increase base concentration, conjugate base concentration increases, that's why rate increases. But can we say rate is equal to K into substrate concentration to base concentration? No. Rate is equal to K into conjugate base concentration only. Rate law depends upon only concentration of conjugate base. That conjugate base, either way you are getting, that is not criteria to me. Either way you may get. But one of the way here base. So with increase in base concentration, obviously conjugate base concentration increases. That's why. So rate of reaction depending upon concentration of base also. We will discuss a little later. Now it is unimolecular from conjugate base only. Looks like E1. Looks like E1. Okay, fine. One molecule only participated now. That's why that instead of that E1Cb, why you are giving another name E1Cb like that? Instead of that, better to say E1 only. Okay, fine. If you say like that, in E1 elimination, first step is leaving group has to depart from the substrate. In first step, mechanism, if you observe E1 elimination mechanism, if you recall, in first step, leaving group has to depart and lead gives carbocation. Is this happen like that? No. Here in last step, leaving group is departed. Am I right or not? So then how can you say this one is E1? But looks like E1. Looks like E1. But what is the difference from E1? Earlier I mentioned the difference from E2. So this is looks like E2 but it's not E2. E2 is considered mechanism. E2 is considered mechanism. But E1 is from E1 CB is from conjugate base. And it looks like E1. But it is not E1 because in E1 first step departing of leaving group. Here is not happen like that. In last step departation of leaving group happens. That means looks like E1 but leaving group is not departed in first step. Departing from conjugate base. Departing from conjugate base. Let us see this reaction. Here X is leaving group. Not OH, here X halogen. Fluorine, chlorine, bromine, iodine. Fluorine, chlorine, bromine, iodine. X you can take any one. Now when you are using OC2H5 minus which is a base. This base seeks proton here with respect to this C double bond O and with respect to this leaving group. This carbon is alpha carbon. This alpha carbon containing hydrogens are acidic. And here also alpha carbon is there. Now with respect to this C double bond, this one also we can say alpha, right? But why this OC2H5 minus is not going to abstract proton from here? So compared to this hydrogen is more acidic because this hydrogen containing carbon is activated by two electron withdrawing groups. One is halogen, another one is C double bond O. Both electron withdrawing groups activates or promotes its acidic nature. That's why base prefers to abstract proton from here and leads formation of conjugate base X minus, and from this conjugate base this negative charge shifts like this and this X has to leave, and what we are getting here? CH3, C double bond O, here a double bond. So we are getting product. So again elimination takes place from conjugate base but not from substrate. Now it is very clear. Sir, you mentioned that X fluorine, chlorine, bromine, iodine. So can you explain rate? Means what happen if fluorine is there? What happen if iodine is there? Fine. If iodine is there, then E1 CB elimination less. If fluorine is there, then E1 CB elimination is more. I am repeating once again. If fluorine is there, E1 CB elimination more happens. If iodine is there, E1 CB elimination not happens. Okay. Why? If iodine is there, which is good leaving group, since good leaving group, it prefers to leave away in first step only. If it prefers to leave away in first step, what happens? Carbocation, means it leads elimination. Or else, when base approaches this hydrogen, immediately this one has to leave, which further leads E2 elimination. So, a good leaving group do not favors E1 CB. A poor leaving group favors E1 CB elimination. So, factors for E1 CB, here what do you say? Leaving group must be poor leaving group. Leaving group must be poor leaving group. First point. Second point, it should possess acidic hydrogen because this base has to abstract that proton and finally it leads formation of conjugate base. So it should possess good acidic hydrogen, more acidic hydrogen. So acidic hydrogen compulsory here and leaving group poor compulsion. So both are compulsory factors. And after abstraction of a proton, formed carbanion or conjugate base must and should be stable. Otherwise that won't happen. Vice versa. If carbanion is not stable, then obviously acidic hydrogen is not there. If acidic hydrogen, more acidic hydrogen is there, which is nothing but formed carbanion is more stable. This is clear. So a conjugate base must be stabilized, and yet beta carbon, say this is alpha and this is beta, beta carbon electron withdrawing group must. So with respect to this hydrogen, alpha hydrogen, beta carbon must and should possess electron withdrawing group. Here C double bond O group is electron withdrawing group. If there is no C double bond O group, in such a case this hydrogen is not acidic. In other words, because of electron withdrawing group only, this hydrogen will be more acidic. Clear? So conjugate base must be stabilized, electron withdrawing group at beta carbon. And OH minus also you can consider in E1CB because of we need only poor leaving group. That's why OH minus favors E1CB, but the same do not favors E2. So simply we can say here, suppose this is a leaving group L, and here some other group, say Z. Here Z and Z is must and should be electron withdrawing group, Z must and should be electron withdrawing group, and L must and should be poor leaving group. In such a case, even CB elimination more takes place. Z must and should be electron withdrawing, because more and more the electron withdrawing tendency of the Z, more and more the carbon containing hydrogen is acidic. More and more the carbon containing hydrogen is acidic. Got it? One, CH2Z, CH2Y. So Z must and should be electron withdrawing group like a NO2 group or CO group or COOR, SME2 plus or CN etc. Such group favors formation of carbanion, and resultant formed carbanion can stabilize by these groups, being these are electron withdrawing. Similarly, Y must be poor leaving group. It should not have good leaving tendency for E1CB elimination, because of if leaving group is good leaving group, as we discussed, it leads either E1 or E2. But being poor leaving group, after formation of carbanion only elimination proceeds. So poor leaving group like OH, OR, OPH etc. So these poor leaving group gives maximum yield of E1CB. If leaving group is good leaving group, that gives other elimination products. Let us have a look here. In this case, C double bond O, OET, it is ester group. With respect to this C double bond O, this carbon is called alpha carbon, and when we are using methyl chloride is CH3 S double bond O Cl. Methyl chloride MsCl, simply notation. It is not formula, only notation MsCl. General we are writing methyl chloride. This one here triethylamine I am going to use as a base, and in presence of this base and methyl chloride, it makes that OH into OS double bond O CH3, just like tosyl chloride. Here OH converts into OMS, just like OTS in tosyl. When we are using tosyl chloride, OTS in general we are writing now. When we are using methyl chloride, OMS, right? Now with a methyl chloride converts into OMS. Later we are using base triethylamine. This triethylamine is base, it abstracts proton from here, and this one goes like this, and this O instead of OH, OMS will leave away. Resultant, the product formed here, conjugated double bonds. Have a look here. This double bond is in conjugation with this one, and this double bond again is in conjugation with this one. This is what we called extended conjugation. Extended conjugation leads more stability. So here you are getting a major product is this one. And similarly, one more thing here, C double bond O groups 2 are there. One C double bond O group is attached further with OET group, which is strong electron releasing, that is nothing but plus M group. Here this C double bond O group is attached to only alkyl group, but not any plus M group. In such a case, out of these two, means with respect to this C double bond O, this hydrogen is activated. With respect to this C double bond O, this hydrogen is activated and this hydrogen is activated. I hope you got the point here. There are two C double bond O groups here. With respect to this C double bond O, this one is activated hydrogen, alpha with this one. And with respect to this C double bond O, these two hydrogens are alpha. Now out of these two C double bond O groups, this C double bond O group acts as strong electron withdrawing group, because of this C double bond O group is not attached to any electron releasing groups, means plus M or plus I groups are not there. But here this C double bond O group is attached to plus I or plus M group. Because of this plus M group, electron withdrawing tendency of this C double bond O group suppressed, right? Resultant, this one methyl chloride, this one converts into OMS, and when we are using pyridine acts as base, it abstracts proton from here, and this one leave away here. Resultant, you are getting double bond here like this, and this C double bond O OET remains as such. So if you observe all these examples, it is very clear. E1CB is stereoselective. Stereoselective means from one isomer you are getting more than one product of which one is predominant. from one isomer, you are getting more than one product of which one is more predominant. So in general, whatever the substrate you are using, ultimately E-alkene means trans-alkene is more stable than cis. Hence E product is major product than Z. So you are getting one product is major, you are getting alkene, right? So in that alkene there are again two possibilities. One is E trans, another one is Z cis. So trans alkene is more stable, hence E product is major than Z. Hence we are saying it is stereo selective because of E predominant than Z. E predominant than Z. Next, intermediate is carbanion. Intermediate is carbanion. That carbanion is participating in resonance with C double bond O. That carbanion is participating in resonance with C double bond O. After participating in resonance with electron withdrawing groups, that converts into double bond. Double bonded carbon. Double bonded carbon is sp2 hybridized. Here if you observe, this electron goes like this, resultant you are getting O minus like that. Now this carbon is sp2. Since sp2 here planar. sp2 here planar. Hence, ultimately, whatever the product you are getting means from which substrate, which one you are getting, that is not criteria. Whatever the initial reactant, ultimately it has to form carbanion, and that carbanion need to stabilize by participating in resonance, which leads further carbon character sp2, means planar geometry. Because of this one, stereochemistry of starting compound is irrelevant. That means if I am going to consider D, are you getting E is major? If we are going to consider L, are you getting Z as major? There is no such questions here. Whatever the starting material, you are supposed to get only E product as major product. E is predominant over Z. So here concept, why you are getting like that? Because of only one reason, that is intermediate is carbanion. That carbanion is stabilized by planar geometry. And next one, less hindered E product is major. So far we discussed that Sage-Jaffe rule, Jayasov rule, Sage-Jaffe rule or Jayasov rule. One more is Hoffman rule. Sage-Jaffe or Jayasov rule is saying that more substituted alkene is more predominant, and Hoffman is less substituted alkene is more predominant. But in this reaction, less hindered E product is major. Now let us see here one example. In this example, first one, C double bond O group is here and this hydrogen is activated. But whenever this hydrogen is activated, here in first step we are using only HCl but not base. After completion of first step only we are using base. That means here beyond of acid base reaction, some other reaction is given here. So let us check first one. We are providing HCl, which is the acid. So being acid, it can donate only H plus. Means here which one is proton acceptor? Again, this oxygen can accept proton by utilizing its lone pair of electron. And one more, here this C double bond O group also, oxygen also consists a lone pair, and it can also abstract proton. Either of these two, but of these two, this one is more acidic, this C double bond O group is more acidic. Resultant, what product we are going to get? So this oxygen gets protonated. Resultant, we are getting compound here Cl, here double bond OH plus and OET. Now this oxygen containing lone pair of electrons will be involved in cyclization. 1, 2, 3, 4, 5. There will be formation of 5-membered ring with one of the position occupied by oxygen. And this oxygen, with respect to this oxygen, this is adjacent carbon consists OH and OET. And next carbon is this one. Next one, this here, this one attached to chlorine. With respect to oxygen, adjacent one ethyl group. This one upon hydrolysis, here given water. So hydrolysis, this OET is going to OET and OH completely convert into C double bond O groups. Here C double bond O and Cl like this. Now it is very clear with respect to this C double bond O, this hydrogen is alpha. So far first step completed. Now second step started here. Triethylamine, which acts as base, and this base abstracts this hydrogen. Resultant, we are getting conjugate base here and here Cl. Now this conjugate base donating electron pair pi electron, there will be formation of pi bond in between two carbon atoms, and Cl depart away. So final product what we are getting here is like this. If E1Cb 2 times takes place, double E1Cb, and both the products are E and E alkenes. Have a look here. With respect to this C double bond O, this hydrogen and this hydrogen, both the hydrogens are active, and when base abstracts this hydrogen corresponding to this OH will leave away. When base abstracts this hydrogen corresponding to that, this OH will leave away, and resultant product what we are getting here, pH, double bond formation, later C double bond O, here double bond and then pH. Now this phenyl group double bond and this double bond O, these are all in external conjugation, and like this also external conjugation. But these two are not in external conjugation, and this what we call the cross conjugation. Have a look here. Acid chloride with alpha position consists one hydrogen. This base abstracts proton here. Resultant we are getting pH C. This carbon consists negative charge CH, C double bond O Cl. Now from this one Cl has to leave away. Resultant product is ketene, which is intermediate for so many reactions. We will learn. This is a ketene. This tabular formula gives complete information regarding in which case which elimination or which substitution preferably takes place. That we came to know very clear here. So let us see. Substrate poor nucleophile like water alcohol, weak basic like I minus or RS minus, and strongly basic OR minus, strong base and hindered. Strong base two cases are there, one is less hindered, another one is more hindered. So for more hindered we consider example tertiary butoxide, and for less hindered normal alkoxide. In case of methyl halide, no reaction. If nucleophile is poor nucleophile, no reaction because of positive charge not able to form upon the carbon here, and ionization do not takes place. That's why we can say no reaction. And for SN2, here weakly basic medium SN2, and for strongly basic medium and strong base hindered also, all these leaves only SN2. And if it is primary and unhindered, not hindered one, in such a case with poor nucleophile or solvent, we can say no reaction or formed product is very less. But in case of weakly basic medium, we are getting SN2, and strong basic medium unhindered, we are getting SN2. Whereas in case of hindrance, with increase in hindrance, obviously elimination leads. That's why E to elimination. And with primary hindered one, here no reaction if nucleophile is poor, and weakly basic nucleophile SN2, and strongly basic nucleophile, whether it is hindered or unhindered, in both cases you are getting E to elimination. And secondary alkyl halide, here with poor nucleophile both happens SN1 and E1 because of via formation of carbocation, but E1 reaction is relatively slow compared to SN1, and SN2 happens in case of weakly basic medium, and strong basic nucleophile E2. Strong basic and nucleophile is less hindered, it prefers E to elimination, and even hindered also E to elimination it proceeds. And tertiary alkyl halide, it proceeds via formation of carbocation. That's why both E1 and SN1 are possible, and even nucleophile is strong, means weakly basic nucleophile. In such case also both happens SN1 and E1. And if a strong base, it prefers E to elimination, whether it is hindered or unhindered, whatever it may be, you are getting E to elimination. And only one example, that is if beta carbon can be stabilized, beta carbanion is stabilized in this case, all whatever the base, whatever the nucleophile, you are getting only E1Cb elimination. So far substitution and elimination reactions are completely finished, and now onwards we are going to learn general reactions by using the content whatever we learned so far, and different reactions of different alkyl halide, and which products you are going to get, major product is which one, minor product is which one, substitution or elimination, that all we are going to learn